Greetings, I'm the Sultan of Astronomy, option E for the IB Physics. And what is a Sultan's favorite snack? Saltine crackers. Ha-hoo! We are talking today about HR diagrams, which you will like because they're very visual. And then it'll be all about parallax and how we can use that to calculate how far away stars are. A very popular diagram for classifying stars is the HR diagram, or the Hertzsprung-Russell diagram. Now you'll notice on the x-axis you can have two things. You could have maybe the temperatures, or you have the spectral classes, which would be based on, you can also think of like the colors from the blues and purples all the way over to the reds. But keep in mind, look at the numbers, 2,500, 5,000, look at 40,000. Both the x and the y are not linear. Your y-axis can be the luminosity, which you can think of as like the power. It is the same thing. It is the how many watts that star is putting out. Or you could also use absolute magnitude, which we'll get to a little bit later. Now you will see that 90% of the stars in the galaxy will fall into this main sequence band right here. We'll have a few that will fall over here that are low in luminosity, meaning they're not very bright, but high in temperature, meaning they're white and giving off a lot of heat. Those are the white dwarfs. Hard to see, but they are kicking out a lot of heat for something so small. But then you've got some things that are very cool, because they're only maybe 2,500 Kelvin, but their luminosity is big, so they must be giant, and they're red. So we give them the creative name of red giants. And then it gets even more creative, because you have some random smattering of stars that are red and really giant. So we call them the supergiants. Now another thing you want to know about the main sequence stars. If a star is cool and not very bright, that's because it is low mass. If a star is very hot and crazy luminous and bright, that's because it has big mass and it is going through fusion at an incredibly large rate. And you will also notice that these are fast-living rock star stars because they will end their lives very quickly. These down here will be long-living stars. They will live to a ripe old age of several billion years. Our sun is right in the middle here. A clever way of finding out how far away some stars is this stellar parallax method. Now you can't just walk outside and try it out in one night because it takes a while. Because what happens is you pick a nearby star like Alpha Centauri, which is the closest one, one of the closest ones next to Proxima Centauri, and you got these background stars behind there which are actually much farther away. And let's say in July, the Earth, which is here, as it goes around the sun, you take a measurement of the star. And on your line of sight, you look right through here. You see all these stars in the background. And then in December, you take another measurement, and the background stars here have shifted. Now, what you've got here, you know that your distance is called 1 astronomical unit, which is always our distance from the sun. We know that number very well. You can look it up. Then, by how much the stars shift, you can get this angle, or this angle. And now check this out. You know one part of your right triangle, the angle. You also know the opposite leg of the triangle, so you can find out what this distance is. Now, this distance and this distance are about the same, because it's such a skinny right triangle. They are essentially the same, and there's an equation that lets you do this easily. The parallax equation is pretty easy because it's in your data booklet, and it's only this, where you've got the distance to this star is equal to 1 over the parallax angle, how much the background stars shift behind it. A catch, though, is that this distance is in parsecs, which is a new unit of measurement which you need to know and to find. So let me just show you. Ba-bam! Here's what a parsec is. It's a very large distance to a star if that star has a parallax angle that the stars shift behind it of 1 arc second. Now, we have to define arc second. But here, first, a parsec, or a PC, is a lot of meters, and it's 3.26 light years. So a light year is big, but a parsec is even over 3 times bigger than a light year. Now, you also need to know that shift of 1 arc second, how big is that? Well, an arc second is tiny. It's 1/3600th of a degree. Now, what that comes from is that within a degree, there are 60 seconds within 1 degree, and within 1 second, there are 60 arc seconds. So if you have 60 times 60, you're going to get 3600. Now keep in mind, 1 arc second is a very tiny angle to measure, and as the star that you're trying to measure its distance gets farther and farther away, then that angle would be even smaller and smaller. And so we can only use parallax to get to stars that are maybe about 100 parsecs away, or a few hundred parsecs away. Any more than that, and you have to use a different method because the angle is too small to use. Solving problems with stellar parallax is pretty easy as long as you remember what units you are working on, because the equation is simply this. So pause this and see if you can solve this problem about Sirius, one of the closest ends to the brightest star in the sky. So hopefully you were able to just simply plug in the parallax angle, because this means arc seconds, and if you do that, you're going to get 2.63, and that is in parsecs. So you got to convert it to light years. So we got 2.63 parsecs, and our conversion factor is that 1 parsec is bigger than a light year, so it's equal to 3.26 light years. Parsecs cancel, and we end up with about 8.6 light years, which is crazy, crazy far, meaning when we see Sirius at night, we're actually seeing it as it was 8.6 years ago.